And the group I manage there has responsibility for GPFS, a center-wide file system, and HPSS, an archive there. So today I'm here to talk about I/O requirements for Exascale. This is daunting, but mostly because I've got a cold, so bear with me here. I got it a few days ago. I wanted to start out with some science drivers here so you get some ideas. A lot of people are still questioning why Exascale or what are we going to see from science. You know, and I've given 3 quick slides here to give you an idea. One of them is what a lot of people refer to as carbon cycle research. So you obviously have you know, research into solar or alternative materials for generating energy. The storage production, fusion, climate modeling, combustion, carbon capture, and you see a lot of the genome work going on right now. Most of these have file sizes today, and NERSC is involved with all of this, in probably the tens of gigabytes for file size in general. The average data set size is probably in the tens of terabytes today. Another one for many of the people here is obviously the weapons research, and they're interested in uncertainty quantification, and so they're after predictive capability, and they want to perturb basically the input to most of the models they have today and see what changes as they do different perturbations, and this is definitely not V&V, which is most people's familiarity with nuclear weapons research today. And it's going to require workflow tools that are integrated with the transport structure to do this. I mean, we're talking huge data management challenges here as they generate ever more and more data that's going to help them and analyze it to figure out what's going on. And a third one I chose is probably not so well known, is a next generation light source. And this is something that's going on at Lawrence Berkeley Lab, I think, as well as SLAC works on this kind of stuff. And basically, you know, if you look at it, this is like an instrument generating unheard of amounts of data. And you see there just the input data rate is basically 4 terabytes a second that they need. And this is something that's being talked about now. As far as when they build it, I think we're still years away. But it's something that they're going to require just to have the system function. So I wanted to give one slide overview basically to hone people in on what, at least what I could glean out of what's going on with Exascale initiative today. Basically, there's, from what I can understand, 2 collaborations, if you will, that are being formed. One's called ACES and one's called ABLE. And these are, you can see the labs there, Oak Ridge, Lannell, and Sandia are partnering, if you will. And Argonne, Berkeley Lab, and Livermore are partnering. And they're designed to collaborate with each other but compete against each other. And I believe they've got roadmaps for each one of those to get some set of systems. I think it's 2 each or something. And so where they'll end up, anyone's guess, but the point is we're supposed to work together to basically, you know, may the best man win kind of thing. And so each are aiming for a pre-Exascale system in the 2015 time frame. And things I've seen says we're aiming for a 300 teraflop system. And we're supposed to shoot for the Exascale system somewhere between 2018, and most people are starting to admit we're talking 2020, maybe even 2022 for a lot of these technologies as to when it'll be available. So the second thing you guys are all familiar with, I think, is the idea of co-design, and they're currently issuing you know, proposals for that right now and being accepted. And this is the idea that software, hardware, and the apps can all function together. So they can sit down in a room, if you will, and figure out what challenges each is presenting with what they can bring to the table. And then the last thing I've seen is a common theme in all of this is the idea of revolutionary versus evolutionary. And I think generally people are on one side or the other. There's very few of us that are either, you know, are both, are capable of both, I think. There's the visionaries, and then there's the people standing there saying that'll never come to be. We need to stick with the norm, and here's what I'll see 10 years from now. And I think both are needed. I think we both recognize that. You know, I think the approaches that are challenging are things like you heard Steve say, you know, 10x at least. most of the components of this Exascale system are going to need 100 to maybe even 1,000x improvements over what they can do today on their standard trajectory. And a lot of the pieces won't be there in 10 years to provide that. So I think that's where the revolutionary comes in. And then we also can't have a machine that doesn't function, right, or only serves one purpose, really. And so, that's where we need the evolutionary to contribute as well. And so I tried to turn this into an I/O thing. If I was the I/O guy, what would I say about the Exascale approaches? And I think for the collaboration and competition part, I think we need to learn, what is working at each of the sites right now. There's a lot of distinct solutions, whether it's a center-wide file system or local scratch, whether it's InfiniBand versus PCIe connections to storage, local disk flash solutions, all these things that are going on right now. Some of them not so tractable at any lab, but coming. And I think we need to look at those and really figure out what's working in each of the lab. Maybe it sounds obvious, but I think it's going to take that for all of us to get through this. As far as the co-design, I think data management has been a topic for a long time, but hasn't really engaged, as far as I can tell, with the I/O people, the hardware people, very, very well in the last, some number of years. I used to be at LBNL, and I saw those guys come and go, and they were successful in producing I/O libraries. Scientists didn't want to use them for a variety of things. How well those I/O libraries worked with the storage is a whole other question. I think, I've heard of, there's Bestman at Berkeley, there's SRM type things, all these things that help with, middleware, if you will, that help with I/O. But they're rarely designed or thought of as in terms of real hardware deployments. And so you always end up with some mismatch. And I think that lets scientists down in the end. So I think we really need to do a better job, the file system folks, the archive folks, at sitting down with data management experts and figure out what's really needed there. And so for the revolutionary evolutionary, some of this is, I think, well known. Disk spindle speed isn't keeping up, and it's not getting any more reliable. We either need something to occur there, or some alternative technology needs to step in. Flash being certainly something that's attractive today, though still cost prohibitive, basically, for the kind of deployments most of these centers have. And then there's still issues with getting it to work with software and all sorts of things. And we need, I know tape isn't often thought of in this, but I'm a tape guy, so tape capacity improvements are needed too. And you'll see towards the end of my presentation some ideas of what I think we'll see or need. And then we need power efficient solutions. I think this is a new thing that's being talked about today, but it's absolutely critical. You heard Steve say 20 megawatts, maybe up to 30. To get there, we need every single component to be thinking about optimizing for power. And data management and analysis solutions are going to be critical. It's not just about moving the data anymore. We're going to need to bring perhaps the functionality that the scientists need to the data. So I wanted to look at a little bit at where we're at today and how we determine I/O requirements. So in general, I think performance needed is achievable. Some amount of money, and I think we're all doing it. We're all meeting the needs there. And the one key piece or note, I guess, is that you do have to work with users and applications. It's not easy. So you can't just deploy the file system, spend $10 million or something, buy a bunch of spindles and have it all work well. It takes a lot of effort to get the users to understand how the hardware is deployed and how best to use it to get that performance. I think designs focus on ratios, and they're aimed at balancing storage resource capabilities. So basically, you'll see in the next few slides, there's a correlation certainly to the amount of system memory available and the speeds and feeds and capacity that you need in your file system or your storage. And there's a correlation to network rate too, I wanted to state. And so I'll show that in the next few slides. And I think there's a lot of time spent kind of doing this, trying to make sure that the data can move up and down the storage hierarchy continually. And I think we're going to need to rethink that. So here is a little bit of an eye chart, but it's basically showing you the storage pyramid: memory, local storage, I skipped flash for now, global storage, and tape at the bottom. And so capacity is why you have the width, and going up of it, up the pyramid, you have latency getting better, or bandwidth, think of it that way. And in general, this is trying to show you the relationship between tiers and how most HPC centers size and time things today. And so I'll just let you look at it for a minute. But basically, the key point I wanted to make here is that the amount of system memory does play a role in the speed and size of the HPC file systems today. And this is that slide I told you where there is a correlation to network performance. And some of this stuff is obviously speculative with the gig Ethernet rates there, or gig E rates. But basically, I just got back from a conference a few months ago, and it looks fairly feasible that we'll have 100 gig NICs by the time we get to Exascale. And this is mostly about the WAN stuff, right? It may have 400 gig, probably in the WAN stuff, but maybe not down to the host yet. And terabit is real questionable, from what I can tell. And that was mostly from an energy standpoint. But network certainly plays a role, and this is archive data. So what you have there on the black and the red line showing you the trend line is the actual amount of data stored up until this year. So it's accurate up to about that January 2011 point, and from then on it's a projection based on the growth. But this is archive data, which you can imagine all data, well, very few of it is actually generated and thrown away, I'd argue. Most of it, if it's of any use, and this may be obvious, ends up in the archive. So this is one way to look at amount of data and needs. And so you get into tens of exabytes of data is what we think most of these archives will be by the time we get to Exascale. And if you look at the Ethernet rate there, it kind of tails off, right, even if we get to terabit. So that's a real question. It'll be interesting to see if we end up at the exabyte level, I guess, rather than the tens of exabytes. Either way, 1 to 10 exabytes is a good guess. And so this is, some of the, at least from my standpoint, some of the major areas of what an exascale system is or needs, the ecosystem, I guess you'd say. So there's the computational system, motherboards, chips. I'm leaving a lot out, obviously, memory and stacked. I think that's a well-covered area within the exascale approaches today. There's a lot of talk between vendors. I've seen numerous talks. And I think there's ideas about how to get there with the compute system. Software, again, is being handled through the co-design initiatives you see. And I think that's a good thing, and I don't think there's much being left out there. PGAS languages and other things that are coming along. So networking, I went to one workshop recently where they seem to be positive about at least the Ethernet rates they'll be able to achieve. Terabit, like I said, is real questionable, at least they're saying, mostly, again, for energy reasons. I can't remember what it was. I think it was 2 to 5x what you currently draw today in watts per port. And that I mean, you're already seeing we got to be more energy efficient, not more of a hog to get there. And then there's the I/O piece, which I think is the tail so far. I'm not sure I've seen a whole lot. We're starting to gain traction with the community, starting to work together, and we need to do that to succeed. And that's the file system, the archive, and frankly, WAN data movement. I think it's going to be necessary. And I'll cover that in a little bit. And so these are the things I'm going to try to touch on in the rest of the talk a little bit. So I'm jumping into what I think are some of the, and these are obviously high-level, interconnect requirements. I think you need power efficiency gains of 10x over present. I talked to a vendor recently who said that the key for them on getting the optics on board on the NIC or on the motherboard is that basically they can reduce the power by 50%. So it has nothing to do necessarily with functionality or what better it can do. Latency is about the same, they said, but they've got demonstrations and it's drawing 50% less power. So I think that's a key factor there. And I think it's especially key when we get to greater than 100 gigabit devices. So they had some sample devices in there, and I think it was 2x what 100 gigabit optics were requiring for, again, watts per port. So I think saving that power is going to be critical. I think you need, on the order of 100,000 to, a billion nodes, if you will, or connection points. And that's a real wide number, but pulled from a lot of different presentations and talks. And you saw Steve, I think, chose somewhere in the middle, 250,000. And you're going to need basically 200 to 400 gigabytes a second internet bandwidth. I think Steve bumped that up to terabyte, a couple terabytes a second. I think most of the things I've seen, and obviously he's aiming high, I think most of the things I've seen are calling for 200 to 400 gigabytes a second. And we're going to need to handle, make these interconnects more resilient than they are today. Either handle congestion or punt on it, I don't know. And enable convergence if possible. I don't see that happening, and I gave this some thought and thought, we really need fiber channel reliability. Everyone hates fiber channel, but the truth is it's still in a lot of the centers, and it still is ultimately very reliable compared to the other network options we have, at least for I/O. We need the IB latency and bandwidth, and we need Ethernet, features, basically routing, manageability, and other things in one network if convergence is going to happen. So some of the file system requirements, again, these are fairly high level, but touch on some lower level points, I hope. So usability is a key factor. We need more than just open read write, I think. And there aren't a lot of object-based file systems out there that provide more than that. But we need to start thinking about that. I didn't put it on the slides, but most people find it takes 6 or so years, I think it was 3 to 6 years before a piece of file system software becomes production ready, and it takes on the order of, I think it was $50 million before that happens. And we're in a market convergence, right, on that stuff, or contraction, I should say. And so, we need to take a look at that and either realize we've got what we're going to see 10 years from now and it needs to be changed, or start to consider what we need to do to get off the ground and get there by 10 years from now. And we need to aid, we need something that aids in understanding for the user the hardware layout and the software configuration to optimize performance. Today, I don't see us getting far away from that, and it almost always, even though we tried to talk about how well these things work, it almost always comes down to, well, what are you doing? Well, why are you doing that? Do you realize the file system, we only have this many spindles, or a single one can only do this, or whatever it might be. So you rarely can actually get away from a user from getting good performance and talking down to that level, so they understand exactly what the file system is capable of and how to get the performance out of it. Power efficiency, I've seen some exciting stuff on enabling the spin down of disks, and I'm not thinking just MAID, but some people a lot of the hardware is starting to put MAID functionality into their devices, and some of it is just simply spinning down the RPM so that, obviously latency goes up, but you get some serious energy savings out of that. I did some quick math, and the I/O subsystem, basically, if we do nothing, is going to require 2.5 megawatts of the 20 megawatts of power. And I don't think that's acceptable. I'm not sure they're planning for that at all. So some resilience features are necessary. When you look at handling the order of 20,000 or tens of thousands of components. Today, most of us run file systems that have somewhere between 5 and 10,000 components with multiple failures a day. It's already getting hard, is what I'm saying. So I think we need to take a close look at how to make that feasible. And we need software failover. There's very few file system softwares that actually do that correctly. It needs to be tolerant of errors. And we need to look at, again, the hardware RAID rebuild sizes. Today, with the size of a single spindle, it's taking them, days to rebuild these disks. And there are software that has, be it chunklets or various, ways of handling the software, or RAID and parity in the software client. So we need to take a look at that. Scalability, we need to handle, again, order of 20,000 devices and up to 1 million clients. And, the target is, I like what Steve said, I think it's a terabyte or more a second, basically, for these file systems. Metadata is a big issue. I think we're going to need to look at, if you had to pick devices that are almost there today for us, either back to solid state, real, memory DRAM type things, or potentially the flash solutions for metadata. I'm not sure it's going to cut it, though, and I can't go into it in this talk, but we've done some testing that shows they're still, a long ways off from being production ready, to be honest. I think today I wouldn't put metadata is our crown jewels, if you will, right, for the file system or the archive. And we definitely didn't, we had the money and definitely didn't do it for those reasons because of the reliability, basically, of the devices. It's not quite there yet. So I can give you a quick thing. We did testing of 3 different vendors, brought in, I think it was close to 20 cards, and of those 20, I think we had 4 that were dead on arrival, 2 more of which failed in some number of months of testing. So, and this is the real expensive, good SLC type flash. And with those kind of numbers, you're not going to put anything you care about on it for sure, regardless of how it performs. And a lot of the software needed changes to actually function with that. Most things are still going on a 512 byte sector size, which flash is not made for. And cost is a big factor. We need more of the system cost basically to basically fund this I/O subsystems. And I'm not sure people are thinking like that. I think the storage is usually an afterthought in a lot of the systems. So here's some archive storage requirements and features to support data management analysis. We don't have that today. Tape isn't often used for that. I think it could be with some work. And again, same thing, aid in hardware layout and software configuration, power efficiency, resilience, all these. So another thing is the WAN data movement requirements. I think petabyte data sets are going to be common when we get to the Exascale era. We're already moving tens of terabytes today between facilities, probably once a month. We get on the phone with somebody and try to figure out how to get 20, 30, 70 terabytes between 2 facilities over the WAN. And it's 10 gig Ethernet today. So I really don't think that's far off of an estimate. And human timescales are very important when you consider the WAN movement. So people look at solutions. If you tell them it's going to take a month to move that data, they really start to look for other solutions if there are any. FedEx, whatever it might be. I think we're talking days to weeks here is probably reasonable, and I think that won't change. I think people need data where they need it in some number of weeks, regardless of how big it is or what's possible or not possible. And so taking a chance here, but I think mounting of other centers' file systems, I don't think it's likely to support science. And my view of it, I think it's interesting. I think it's exciting to talk about. And we're certainly, looking at it with other centers, mostly Oregon, I think, at the moment. But, I think there's some severe challenges here that are accepting from the technology that make this unlikely to support science. And so those are, federation of accounting and users. You're going to need federated accounts, right? If you mount somebody else's file system somewhere, UID1 is not UID1 at their site. And I think that has been an intractable problem to solve in the last, decade. So unless we figure something out and figure out how to federate accounting, I don't think it's going to happen. And I just don't see that happening. It's been talked about for a lot of years. I think you need additional security for devices on someone else's network, and I think it's pretty scary to think of your file system being mounted there or your devices being seen by another, at another site. I think you also can't change the speed of light, right? So changes to enable high latency operations as the norm. Maybe you can get all the devices in the path to play friendly and make it work. I think it's been demonstrated, but again, that latency is going to be there, and I'm not sure how usable that is for most centers. So I believe that most of it is still going to be explicit data transfers. I think most people are still going to push the data to and fro between sites. Another thought that I didn't put on here, but is the size of these file systems. It's unlikely that every center out there is going to be able to afford, be it energy or budget-wise, the size of file system that's needed on an exascale system. So, people at other sites are going to be operating on a reduced fraction of that, so they're not going to need to push the raw data around, but some subset of that. So with explicit data transfers, you need a high throughput network, configured to optimize the data transfers. Today, this is what I'm familiar with is the Energy Sciences Network between the Office of Science facilities and DOE, and it's the SDN network. I don't know what they're talking about for the future, other than improving that, obviously. Software to aid in unattended data movement. Today you have things like Globus Online, It's an interesting software where it solves some of the installation problems people have had using grid FTP and other things. And basically, it's a software as a service. You go to this website, you select a couple endpoints where you want to move your data to, and it basically does it for you and does a callback to you, I think, when you're done, so that, as failures occurs, it retries and all sorts of stuff. And I think that's the right direction to go. It doesn't mean someone has to sit at a terminal and monitor errors for days or weeks. And then there's storage resource managers that are in use by a number of the projects that compute at our facilities. And one example is BestMan. And it helps them today do the same thing. They have local caches of disks at site that they define, and it helps push data to and fro and cache just the right things between on the kind of storage that they need. And it brings archives and file systems and all sorts of things together into one pool of storage for that project. And you're going to need dedicated servers close to site's border. And today we've got some demonstrations of that. We call them data transfer nodes, but they're basically very close to the border. Very few hops basically to get to that center's WAN connection, and they've got all the storage that's available on that center on that node, and they're reserved for that purpose. And so that really does work. At least it has for the last few years. It's worked for users. So bear with me. I'm going to do I'll try to go through these as quick as I can, but I'm a tape guy, so I got to give you a little bit on the archive. So we did a workshop, almost 2 years ago now, and that's the cover page for it. But it basically was trying to evaluate HPSS specifically and determine if it's fit for the extreme scale era. And I try to point out some of the key points out of there so that you get some idea of what this system might look like for the archive. I think it's going to be between 1 and 10 exabytes of data 10 years from now. I think it's going to need annual growth in the tens of petabytes range. And I think it's going to be 1 to 10 billion files in these archives. The ingest bandwidth is still going to need to be about 10% of the scratch file system speed, and you could see that from that triangle I gave you a while ago, the pyramid. So which puts us at basically 100 gigabytes a second peak and tens of gigabytes a second sustained. I think it's very feasible from an archives perspective. So the metadata speed is probably one of the hardest things for the archive today and in the future. You're going to have petabyte-sized metadata, and file operations are generally around 10% of what the file system's capabilities are. So we're already planning for multiple metadata servers. And this is all based on, at least for HPSS, DB2. And I think I think you guys had a presentation last year on peer scales. Things like that are very interesting to us because currently, DB2 partitions based on Ethernet, which just isn't going to cut it, I think, if you're talking about petabyte-sized partition databases and needing to get an operation complete in some reasonable amount of time. And so the network's going to need to be capable of 100 gigabytes a second basically to support these archives, and they are all network attached. I know very few examples that aren't on the network, and I mean Ethernet. So I think we've identified we need some serious work on data management with HPSS. And with this, you've got data discovery, it's a middleware challenge, data mining, a middleware challenge, and basically data set operations. People are really tired of the traditional Unix, I think, namespace and per file and where it's at and who it belongs to and what I need to do to get my data set. So I think people are going to start thinking about things in terms of, run 1, run 2, whatever, and delete run 1, move run 1, things like that. And so from what I've seen, my familiarity with GPFS and HPSS, they've got a start on this. It's got a long way to go, though. And I think you need to look at system management. It's not very glorious and probably not particularly interesting to networking or the interconnect, but system management requirements, you're going to need to manage thousands of software processes in a single server. It's hard to do with the screen real estate we have to look at 1,000 devices in any meaningful, quick way to determine what's going wrong. So we're going to need to rethink that. We're going to need to look at managing multiple metadata servers, and maybe it's like distinct systems. But that's hard when you're the administrator to figure that out and what's going on if you've got tens or hundreds of these things. Logging subsystems, so we're going to need to handle thousands of processes, each of which have hundreds of threads today. And so, we've got tens to hundreds of processes today with hundreds of threads. Some of them actually have thousands. It just depends on the site. But, that's a challenge in and of itself, too. How do you do real-time logging with that, right? That's you can stare at and figure out what's actually going on right now without waiting 5 minutes to get the answer. So we need to continue scaling and real-time monitoring, on a very large, complex system. And we need affordability at scale. So this is giving you a sample for that I think it's 10 exabytes of data. We believe we'll have an 80 terabyte tape drive in 10 years. And that's going from a 5 terabyte tape drive today. And I think that's reasonable. If you look at a midpoint, IBM did a design that showed a prototype 35 terabyte tape, I think they said by 2015, 2016. So I think there's multiple points that say this is fairly reasonable to expect. But it's going to require 90,000 tapes, which you see the punchline there is $27 million in annual tape budget if something doesn't change. So that's got to fix. I guess feasible, but a lot of money for the tape alone. And that's a device that we believe will be there. So it's just a matter of budget at that point. And basically each tape drive, I think that's just an interesting point, will be somewhere around 600 megabytes a second for a single drive. So some final thoughts I had, trying to pull this together a little bit. I/O is definitely a major part of the Exascale system design. There are networking initiatives underway. The co-design proposals are being out there, or put out there right now and accepted. And storage basically requires evolutionary. We need to consider where we're at and where we're likely to be, and we need those file systems and archive systems that are, to continue improving. And I think some of them will meet some of the characteristics we see. And we need revolutionary storage for some of these other things I've listed. Basically, performance improvements over current rates, reliability improvements, power and efficiency improvements, and moving the analysis closer to storage. That's it. Do you have any questions? Go ahead.
You see, so this is a different conference. You were saying that you saw a fiber channel being more necessary for reliability. What do you see necessary for InfiniBand to move into that position being transport for storage?
We're already looking at it for basically, think of it like the center-wide network, basically, and connecting. I mean, most of the clusters today have InfiniBand, so we're trying to figure out how to make an InfiniBand storage network and connect into that. Some of the storage devices have InfiniBand heads today, very few. I don't see that providing much, me personally. I mean, most of us have fiber channel infrastructures, have paid a fair amount of money for that and want to reuse it. That stuff's been there for 5-6 years, don't see it going away. I mean, that's replacing everything from the ground up. So I just don't see us doing that. I see us trying to leverage that. But to be honest, I've got a huge fiber channel SAN at NERSC right now, and it's not going to scale. So, I mean, I need to look at things like IB for basically between the clusters to those storage servers. Does that help? Okay.
You mentioned about some security requirements for GitHub, some
So it depends how you export that file system, if you will, to another center. But I think the scariest is to consider making your devices available to that other center, which you don't have to do. If you did that, currently today we've got, I can't think of much to say to the point other than we've got basically some of our clusters at NERSC able to see the storage and write from multiple spots, multiple clusters. And already today, that's scary as anything for us, given compromises on that host or what can happen, which can affect the whole, the file system across the center. And think of root compromises. If they get it on one system, they've got devices, they now have a root compromise on the file system too. So I'm just thinking that as we go to allowing our resources to be mounted at other centers, it's really extending at least your policies, right? What you think are okay, and that's different at every center today. I mean, you won't get any one center to agree what's reasonable, and it doesn't matter about performance, right? It's almost anti-performance, and what they'll allow to occur. So I think those are things we need to consider if we need the performance. Okay, thanks.
Okay, thanks very much.
Sure.